Hello, everyone. Thank you for coming to the Action Seminar. And today it's our great honor to have Professor Liu to give us a talk on the cybersecurity, action security in the power grid. And Professor Liu is well-respected scholar and researcher in power and I should say electrical power. And he has a long list of his actual achievement. I don't want to highlight all the one. Currently, he is a professor in the Virginia Tech and also the director of the Power and Energy Center. And he made a lot of achievement, received a lot of medals. I think it's 20 years ago or 30 years ago. So you can say this is very special, great actual achievement and accomplishment and great job. And recently, I think a power grid and the power reduction right now is very important part of the cyberphysical system, right? So Professor Liu is going to show us actually his view about actual cyber-physical system security in the power grid. And this will be great talk. And let's welcome our speaker.
Great. So thank you very much, Junie. It's my pleasure to be here. And I know we set up this seminar a few months ago, but it took a little while for this to happen. And I'm really pleased to have this opportunity to meet with you, so to speak, and be able to discuss this topic about power grid cybersecurity. And I remember when I started working on this problem, cybersecurity of the power grid, that was 2006. And there wasn't much of research to speak of at that time. There were some papers about the doomsday scenario. If there's a cyber attack, they're going to take down a lot of things and it's going to do a lot of bad things. But I think there is an important milestone. One is the government has a project, I think it's called Aurora Project, which actually did a test at a national lab setting, which actually shows there's a model of a substation, and a cyber attack launched from that model substation can actually damage the diesel engine, diesel generator. So which means cyber attack can actually damage the physical system components. And I think that was an important wake-up call. But then, of course, since then, a lot has happened, and particularly, you will see, we were, let's see. Good. So particularly, well, now we are looking at Ukraine power system, and this is not meant to be matched with the current events today, but this is possibly the first major attack, publicly reported attack on the power grid in 2015 that actually caused a major power outage, and it happened in Ukraine. And so, and it's interesting because before that we know it could be done, and we know the power grid has come to a stage where the cyber system is important, and it's the new class of threats that's coming to the power grid. But this is the first publicly reported major outage, and so it's an important milestone in this research topic. And how did this happen? If you, let's see. So if you actually look at this, if you look at these slides, the title of the slide is interesting. It says cyber security of the power infrastructure. So that cyber, because normally people's impression about power grid is you have power plants, you have substations, you have lines, power lines, you have all these motors in the lab, etc. That's what our image of power grid. But there is actually an important IT and communication infrastructure that sits on top of that. And this picture is intended to show that. And what does that mean? There is something called SCADA, which is supervisory control and data acquisition. So this is the computer and communication system which allow power grid to acquire data, do data acquisition from a widespread power grid and collect them into a control center. You see here control center A, control center B. And this control center collects the data, make the decision, and then they send the control commands back to the substation. And this box on the right-hand side represent the substation. So you can see the black color represent the physical components, circuit breakers, transformer, etc., etc. That's the power grid. And then the red color and also the black dotted colored communication system and protocol that represent the cyber system. So this DMP3, this is the protocol between control system and control center and substations. And there is this ICCP, which is the protocol between two control centers or between different power grids. And so you can see here, the power grid relies on that communication system and IT to run the power grid. And therefore, there are vulnerabilities. So let me go back one slide. And so what is that? And power grid has been around for more than 100 years. So what is that cyber vulnerability? So you can say the SCADA system exists from probably 60s, 50s, they're already there. But the software, the sophisticated software to run the power grid, they came in probably from 70s, 80s, 90s. And but then from the 80s, there is a trend for the system, computer communication system, to be more open system, and also more standardized. So before that time, 80s, you go to a power grid, look at their real-time computer system. It is a special purpose real-time processor. There's a primary, there's a backup, and they look different from what we have today. If you go to a control center today, look at the computer IT equipment of the power system control center, they look like your desktop at home or any lab at Purdue University. It will look the same. So that's because the technology is more standardized, and also there's a widespread availability of technical information. And there's a specific reason for the power grid, because this equipment, the operation and control IT equipment, it's a SCADA system, or we call it energy management system, EMS, or distribution management system. In the whole world, there are only a handful of major multinational vendors, which means any country, any big power grid, you're trying to buy such a system, most likely you're going to be buying from one of them, and you can count with two hands, the multinational vendors, which means there is not much of a secret, because what you know is what many other people know. And that's what this widespread availability of technical information means, because there's so much similarity of the systems around globally. What you know is not much of a secret. Many other people know that. Okay, so that is why there is that vulnerability that's sort of built in industry. And the power industry, or the regulatory agency, is doing something. This North American Electric Reliability Corporation is called NERC. In the power industry, NERC is the agency that sets the standards for North America power grid. And so cybersecurity as an important topic is already recognized. So these are the kind of standard that has been set up by NERC, and the industry power companies, power systems have to abide by these standard, because it is not voluntary. So it's a standard, and so there is every 6 months or so there will be some kind of auditing to make sure you meet the standard. However, the standards here, if you look at these standards, they are kind of general, high level. For example, critical asset identification, and then personnel training, and physical security, and incident reporting, and response planning, etc. So these are kind of the general guidelines. So essentially what these guidelines says, you shall be good, but it does not tell you exactly what you have to do. There is still a lot of the a degree of freedom for the industry to decide what they do, but they have to meet this requirement. So there is not a standard practice that the industry is following about how to protect your system and how to mitigate the cyber attack. But does it happen? I would not say there's a successful attack happen often, but I can tell you the attempts of this such attack is very much there. So just a few months ago, one of the big power grid manager told me their company has been there has been 2 billion attempts on the power grid, and so you can see there's a lot of interest in the power grid in that sense. Now, and so what do we need from a technology point of view and from a conceptual point of view, research point of view? How do we increase the protection of the power grid? So if I try to summarize the state of the art literature of this area, then you can pretty much say on the transmission system, there is a data acquisition device, which is called phasor measurement units, which actually was invented by Virginia Tech some 30, 40 years ago. And SCADA, this is what I just mentioned, and substation automation. This is the software and IT technology that actually runs the substation. And in the distribution level, the lower voltage level that connects to all the customers, then we have distributed energy resources. This is about the renewable energy and energy storage. Then advanced metering structure, this is the smart meters. And the smart meter is connected to many, many customers in the US. So it's safe to say more than 50% of the electricity customers are using smart meters. So somewhere outside your house or apartment, there is a box there. That's a smart meter, and that smart meter is connected by communication. And every 15 minutes or 30 minutes, is sending the energy consumption data to a power company, and they use that for bidding. But they also use that for remote access. For example, if you have a power outage, you call the power company, and they check your customer information, and they find that you have not paid your bill for 3 months, then they know. So your power was cut off through that smart meter box, and so they will laugh at you, and you better go home and pay your bill. So, and then distribution automation, and this is the last 10 years or so. A lot of the remote control switches and devices on the distribution grid has happened in the last 10 years. So, and because they're remote control, there's vulnerability. So you can see from these different categories, the power grid has different pockets of communication IT system, and unfortunately, it's not one system, so it's not seamless. It's different systems, and so there's a question of whether or not you can one attack, one can protect all these systems as a whole. And then in terms of research topic, there's a vulnerability assessment, and that includes modeling the system, impact analysis, and also identify the weakness, and then intrusion anomaly detection. So this part is still in the early stage, and a lot of what I talked about is this intrusion and anomaly detection. And then there's a mitigation. This is when it's attacked. You know something's going wrong. How do you do it? And if it happened in the cyber system, how do you do it? If it's happening on the physical system already, how do you mitigate that? So, and now in the power grid area, we are very used to finding a list of potential, we call that contingencies or events. So for example, severe weather is an event. Cyber attack will be another event. Next one could be earthquake, etc. And so we have a list of these contingencies, and the normal practice is trying to find trying to find the worst case scenario, because the reliability of power grid is very important for the society and economy. And so we want to look for the worst case, so we can actually try to fix the bottleneck and plug the hole of the threats. And so what's new here is the cyber attack should be considered a new list added to this master list, which we already have over many decades. Most of them are weather-related events, hurricane and earthquake, but now this cyber vulnerability has become part of it. And so if I have a way to create a list, and then I can measure the vulnerability, then I will have a much more scientific way to figure out how we can mitigate and how we can improve the cybersecurity of the grid. And so this equation simply means something very simple. It says, if you want to measure the impact of a contingency event, as I mentioned, you need two things. One is the probability. How likely can it happen? Two is the impact. What does that mean to the power grid if the attack is successful? And so these are the two symbols that represent the probability and the impact. If I can find these two numbers, quantify them, and I add together all the access points, I will get a vulnerability measure. And so if I go to the boss of a power company, I said, we need to improve the security. And the boss says, okay, why do you need 10 million to do that? Or I said, because with 10 million, I will be able to improve the vulnerability from X number to Y number. And that means the power outage will be reduced by how much, and not to mention the public reaction, just that reduced power outage will be enough benefits to cover that. So that would be that's why we need the vulnerability quantified. And so then first thing I need to get probability. So how do we do that? And here is a simple example. This actually represents a firewall. We all have firewalls on our computer systems, right? And the firewall is simply a set of rules that define who gets in, who cannot. And so this picture shows rule 1 defines who can get in, access, and another group can get in, and the end group can get in. And then if you don't meet any of these rules, then it will be denied, and you can keep trying as the attacker, you'll keep trying. And so if I collect enough data, I'll be able to see how many attempts and how many successful, how many failed. And by that statistics, I'll be able to find the probability. And so for this particular firewall, I'll be able to find what's the probability that the attempt to be able to successfully access the system. And that's how you get probability. And how do I get the impact? So to get the impact is much more complicated because we are dealing with a cyber physical system. Cyber is the SCADA system and other related information and communication system. And the physical system is the power grid. And traditionally, we know how we simulate power system a lot, but we don't simulate the IT communication with the power system. And so that is the problem, the model of the cyber system and the integrated model of the cyber system plus the power system that's missing. And so this allows the research there is to find, be able to integrate those two systems. So I'll be able to hypothesize cyber attack scenarios, and then actually simulate how the attacks are launched and how they access the physical power system if you don't get intercepted, and what it means to the power grid. Okay, and that is an important research topic. And actually, this is the bottom of this is a PhD thesis of one of my students, Stefanov, and this is 2015. So that's when we actually have a systematic way of a cyber system model, SCADA system, and the power grid, and link them together. Okay, I'm not saying that cyber system is not there. The SCADA system has been there for a few decades, as I mentioned, but the software model which allow you to do the study is not quite there. Okay, so this is a picture representing the software model I'm talking about. So the bottom is easy, that represents the power system. And the red, the three layers on top represent the cyber system. So there's a transmission operator, there's a control center level, there's a substation level. So this transmission level will be like the big power grid. So for Virginia here, it will be PJM interconnection, okay, and maybe you too. So that PJM interconnection is the highest level transmission grid operator. And then the next level will be local power company. So for here, it will be the Appalachian Power, which is a branch of the American Electric Power Company. And the bottom here will be the substation. And one substation is right here at the on campus, Virginia Tech. And so we have to have a software model of this. So you can study, you can look, if you look into these boxes, it's not power component, it's IT components. And so what we did is we actually use the computer queues and to construct the model of the IT model here. And that represents how the data is acquired, how it's transferred to the control center, how communication latency happens. And if anything there is attacked, like some communication link is destroyed, or there's a distributed denial of service to increase the latency, then how do you actually model that, and what's the impact on power grid? That's where they came from. And so, and once I can integrate that, so here is an equation. Don't worry about this equation. What it means is that I want, for the physical power grid, I'm watching the performance, the frequency. At home, you want 60 hertz. This is the load. At home, you want how many kilowatts you need at home. That's what you need. And then there's a voltage. You want 120 volts, you are watching that. And there's a currents on the power lines. You don't want overloads on power lines. So by watching all these from simulation, you're able to see the impacts on the power grid. For example, if the grid is losing a lot of load, that will be this index, this term will have high value. If frequency begin to decline, then you'll see a high value represented there. And so this picture shows you how we measure the impact on the power grid. And then, so the next one is how do we prevent the intrusion? And I mentioned this intrusion detection. The concept is very simple. What it means is traditionally, we have firewall to protect the substation. You see a firewall here. But the firewall, as I showed you a few minutes ago, it's an access control. It's like, so access is like a door. Who can pass, who cannot pass is a security guard. But then once you get in the door, what you're doing, you don't know. And that's why this intrusion detection is more like an intelligent system. You read the data log from the IT system communication. And from there, you do your analysis to see if there's any anomalies happening in the substation. And that's the purpose of this intrusion detection system. And to be more specific, in the substation level, I will mention two things, the red color here. One is this thing called modified goose message. This is a substation IT network. And whatever that means, this red bubble here means falsified operational command of circuit breakers. So this is very important because this, like what happened in Ukraine in 2015, to open that circuit breaker, I need to be able to either use the authenticate control command, or I can falsify control command, convince the system that the breaker should be open. And that's how you disconnect the load. And on the right hand side, this is the fabricate measurements. So this is in a substation, and I will show you an example later also. You look at the measurements, the volt, let's say a voltage, and I take the voltage and I sort of do a random falsified measurement and give it, let's say, very high voltage and send it to the control center. The system operator sitting in front of console, they look at that and say, oh my God, there's a big problem. and they start react, and they start to do the control actions and trying to bring down the voltage. But that also contribute a problem, because the problem is not is fabricated, but the actions are real. So the damage will be done because of that. Okay, so now how do I simulate this type of events? This picture shows a cyber physical system simulation testbed. So on top here is a power system simulation tool. We call that power system simulator. And on left-hand side here, this is a simulation of the information communication command. So I can synthesize the communication command with the software here. And right-hand side, this bubble represents the research. So I want to analyze the similarity of attack and impact analysis, etc. And they are connected by this yellow box, which give you a real-time kind of interaction. So if I want to open a breaker, this yellow box go into the power system, actually change that breaker status and say, hey, you're open now. And power system simulation will start to do the simulation and tell you what happened. Okay, and that is what I'm going to show you here in this very simple demo. So left-hand side is a power grid. Okay, this represents the red color means breaker is closed, and this white bar means the substations. So you can imagine a big power grid spread in a very wide geographic area, and many power lines. And circuit breaker means red means the lines are energized. And later, the cyber attack is going to open circuit breakers in 7 substations, and that is a coordinate attack or multiple attack. And through that, it's going to take down some generation, shut down some power plants, and because of that, the system is not able to serve the load because load is the same, and so frequency will begin to drop and voltage will begin to go crazy. And that is what you expect on the right-hand side, because I'm now showing you a cyber left-hand side, and right-hand side is the physical system simulation. That's the impact on the power system. So this will answer that question of the impact and when we talk about vulnerability. So let's go. So attack has happened. This represents the attack packets are now being sent in substation, and it happens very fast because it's IT. And the right-hand side, you can see power grid is also reacting because the frequency is falling and voltage is also falling. And then you can see some of the breakers in the flashing substation, the breakers, instead of being red, they are now empty, dark boxes. That means breaker has been opened. And so some generators, that generation is lost. And then load is still there, so frequency is dropping and the system is falling apart. And when frequency go down to about, if you can read it, 58%, 58 hertz in the power grid, 59 hertz, 58 hertz, that's already very serious. And so you can imagine the automatic load shedding equipment in the substations, they will be triggered and you start cutting load. And at home, you feel the power outage. And this is what happened in the Ukraine power grid. And you can see the power outage. And now the question is, now what? Okay. So the now what, first step is the how do we, the mitigation. So how do we prevent something like this? So if you look at this picture, there's a substation here, the IT system of substation. And there is a yellow box here. It's called Anomaly Detection System. And that is actually the result of a couple of PhD theses. And the idea there is you look at, you develop the logic or the intelligence system, if you would. So it's based on logic or intelligence. You look at the commands going through the substation, and you can identify which one is normal, which one is abnormal. And that's because you can recognize which command has been falsified. A simple example is there is a type of a replay attack, which means you take an authentic control command and you bring it back later at a later time, and somehow the system is not able to catch that. And so that's one simple example, but there's a lot of logic in this yellow box. And actually, on there's a small red box at the bottom here, or lower right. It says this number here. This actually means the number of abnormal packets that have been captured. And so you can see, by being able to detect the anomalies, you'll be able to prevent these packets from reaching the circuit breaker. So that's how we mitigate the system. And another important thing here is, by being captured here among that 1,500 more packets, by being captured here within the substation, they have not hit the physical system yet, which means the circuit breaker is still closed. Control center operators don't even know something has happened, because you are able to work in a cyber system level and being able to capture that attack commands within the cyber system. And that's the key, because then the physical system is not impacted. But that also means it's a big challenge from technology point of view, because within the cyber system, you are working in a millisecond level. And so everything has to be fast, no matter how smart your algorithm claims to be. All right, so here is another example that shows the coordinate attack. So the picture here represents actually 4 different counties of a state of Washington. I think you can see George picture here. So it must be state of Washington. And so this is trying to observe what's happening. This is in the lab. This is not a real system in the power grid, but it is to show how you monitor the cyber attacks. So you can see there are 4 attacks here. And if you look at the left-hand side box, it says abnormal behavior, critical relation, geographic relation. So from the attack here, it's not in the same box. So which means it's not the same county. You're not trying to attack the same county, substation in the same geographic region. Rather, by the analysis here, you are trying to attack the critical substations. And that's what critical means here. So these are the highest voltage transmission substation that carries a lot of power. So any damage on these substations, the impact will be very severe. And that's captured here. It's identified as a critical relation. And so this is how you conclude there is a coordinate attack in this case. Okay, so you're trying to look for the relations that tie these attacks together, so you can tell these attacks are coordinated. And this is just a picture to show how to identify the coordinate attack. The relations I'm talking about: abnormal behavior, critical substations, geographic data, etc. So you take all the information from the substation and run through these algorithms, and that's how you get the relations attack. And so the next problem is what I mentioned, the measurement-based attack. So I mentioned you sort of intercept the measurements in a substation, and here is a good example. Let's say there's a backdoor access to the substation, okay? And in a substation, there are A here means you collect the currents. So electrical engineers know this means currents, amperes. And there's a V here that represents the voltage. And so the analog waveforms converted into digital formats and travel upstream the computers and IT equipment, and then the communication protocol, they get sent to the control center, all right? If there's a backdoor access, what could happen is I put some malware in the substation, and along the path of the measurements, I start to fabricate, change the measurement and make it just like that case I mentioned. I create this unbelievably high voltage, which will make the system operator sweat. And because time is so fast, they don't know there's a cyber attack yet. So this could be that one example. And how do we detect something like this? This is a research. This is a more research methods, and I think we have done we have done that, how to identify these measurements. So how do you know these measurements doesn't make sense? And so falsified measurements, they can mislead system operators. That's what I said. And so we need some intrusion detection system to detect how these measurements have been, or how these have been falsified. And so in terms of the analytics, what it means is I have an intrusion detection system, and data collected from the grid. For example, I collect this SCADA system data or the phaser measurement units I mentioned. And then I have network data. This is IT network data. And then I have a intrusion detection system. And the intrusion detection system is based on the law of physics here. That's why this physical rules, it's not very good English. What it means is the law of physics. And from there, I'm going to detect these measurements don't make sense because they violate the law of physics. And then I'm going to figure out which data, which measurements should be discarded before they go out of the substation. And here is the law of physics we are talking about. So if you're an engineer, you probably will hear your basic electricity class. There's a Kirchhoff's law, current law, which means all currents entering one point on the electrical circuit shall sum to zero. So what comes in must go out if there's no storage of electrons. Two, there's a Kirchhoff's voltage law. It means if you go around any loop in the electrical network and find the voltage drops along every line, every link, and add them together, it shall be zero. That's what physics says. And Ohm's law says, if you look at every power line, they have a resistance and impedance, and the voltage drop should be proportional to the current going through that, and that proportional constant is the impedance or resistance and reactance of that line. So these are physics. They have to be met. And so what it means here is, okay, fine. If we know that, then in the substation, I'm going to collect the data from substation, and I'm going to share data among substations. And so there is a protocol, the communication protocol, which allow you to bring data from other substations. And if I can take that substation data and do my analysis, and if it don't meet the law of physics, I know this is fake. And so that's a simple idea that electrical engineers would appreciate. And so, and you can argue, of course, I can fake the measurement in such a way that they still meet the law of physics, but then the attacker will be very sophisticated. And also it's still questionable whether that can be done practically. All right, so let me quickly mention, I'm a little bit out of time, but I can give you an example here. So here is the renewable energy. So I'm trying to say there are PV facilities, solar facilities, and today we have a lot of them. Right outside my window, there's a few 100 kilowatt solar sitting on top of the parking lot. In Virginia Tech, we have a couple million megawatt solar panels that's being added around campus. And so the question here is, can I attack these PV facilities? Because the PV facilities are generators, it's just different type. So if I attack these solar facilities, a few megawatts would mean I lose a few megawatt of generation. And so what does that mean? And so how would that happen? So the question is, yes, it's possible. It's not easy, but if you monitor the IT activities associated with that monitoring of that solar facility, then you see there's someone trying to connect and heavy network traffic, and the processor of the IT is down, performance is down because very busy, such as denial of service attack. And then you conclude maybe there's a flooding attack. So you build a dictionary, and then you observe the activities in substation, and you'll be able to find what's happening. And what's the real impact? This is the test bed we have here at Virginia Tech. You can have an IT communication system and power system simulation, and that will allow you to figure out what's the impact. For example, this says if you lose a power converter, if you lose a solar facility, you also lose a smart inverter control capability. And so the voltage profile of that distribution grid will suffer. And this means the voltage profile along the geographic distribution feeder, that voltage profile will drop. And this is what that picture means. So I think I will give you one, given that I have 31 seconds, I will just mention in the distribution level, what we want to achieve is every node will become an intelligent agent, all right? And the nodes will be able to share information. So if one node is attacked, they will share information, so the other node will be informed. And somehow by working with each other, teamwork, I call that neighborhood watch system. And so these intelligent agents will be able to work with each other. And through that, so if one node is attacked and I can detect it locally, then I broadcast to the neighborhood, and the neighborhood will see how likely am I going to be attacked the next step. If it appears that my features are fairly similar to the last one, then I might have to lock down communication or restrict the communication, so I will not be the next victim of this. And so this is an interesting concept, because that does mean the power grid will be smarter, and we have this multi-agent system, and they share information, share intelligence, and for the common good, protecting, making the power grid more secure and avoid the outages. So I think I ran out of time, but I want to conclude that I think what's interesting here is we no longer study a traditional power grid. Now we have to look at power grid as a cyber physical system. And that's why the title of my presentation is not cyber security of a power grid, it's cyber physical system security of the power grid. So with that, let's see if we have time for questions. I do see there's something in the chat. So if you have any question, please send it in the Q&A or the chat. So, Junie, I'm back to you.
Yes, thank you. So for all the attendees, if you have a question, yeah. So okay, they allow me to open the window. So someone, Paul, I can read the question for you, but for others, please type the question into the Q&A. So Professor Liu, would you want, actually we have two questions, but would you want to answer there's one question pop up in the Q&A.
I see this one on the chat box. So can I start with this one?
Oh yeah, if you want to answer both, fine. I plan to actually ask Paul to pose the question to Q&A, but it's okay. It's up to you. Yeah.
Well, let me start with this one on the chat box. It says a transmission system operator is not likely to act on a single fake measurement because their state estimator will flag data as problematic. Have you thought about leveraging the energy management system state estimator for your measurement intrusion detection system? So this is a very good question, because it does show the importance differentiating between cyber system and power system. And the reason I said that is when I see there's an attack from the state estimation, this attack already started from the substation, arrive at the control center, pass that software of state estimator and show you there's a problem, but that's too late, because that data already get to the control center. And if it's a raw data, the operators already saw that, because the operator saw the raw data on the screen. And if they are going to react to the raw data, it might have already happened. And so we cannot rely on the state estimation is good because it will help you improve the quality of further security analysis of power grid, but it will not be able to help the operator in mitigate an ongoing attack or an attack that has not been processed by energy management system. So I hope that answers this question. There's another one, Q&A. So there's a question from the RAP. What do you believe is the first step to securing the grid? That's a very general question, but also an excellent question because, okay, so what's the first step? I would say, you know, the power grid, because the power grid has been there for more than 100 years, as I said. And we can run the power grid even without radio. So 100 years ago, imagine, there's very little communication, and maybe the phone was just being invented. Yeah, and yet the power grid was running in a local level. And so we know how to run the power grid with minimum communication. But the question now is that we have added so much of the information and communication technology that the vulnerabilities has increased a lot. And so what I'm trying to say is at the time we were adding this ICT, communication, IT, all this new technology, we call it smart grid or whatever, resilient grid. We are adding all these technologies, but then the power grid itself, there was no concept of cybersecurity when we put the power grid together. And it operates for more than 100 years ago. So there's a lot of vulnerabilities that has to be plugged there, because today all components, you know, even power components we're adding, they become connected to the network. And so everything we are adding sort of added to that connectivity, but is that secured? And so I think as we add the ICT, how we look at the new IT technology and the old power grid and make sure that that integration will consider the old power grid and make sure it's secure. I think that is a gap that we have to bridge first. And of course, we are adding all these firewalls and encryptions and many other things that cybersecurity area is adding for that technology. So we have to catch up. But as I said, the big gap is that we have a power grid that's running for 100 years. And how do you make sure that it would be secured from attack from the cyber layer? And that is a less understood question.
Actually, well, I will have one question because, you know, so can I ask one question? I thought we are kind of run out of time, but you know, someone else has a question. Would you want to comment, Professor Ashen Liu? Would you want to take a look about the chat? Because Paul has some comments. Well, I don't know if you want to comment that.
Sure. So the comment says, I'm sorry, have to disagree. Operators concerned with reliability. Can you hear me? So
yes, we can hear you. Yeah.
Operators concerned with reliability tend to operate off of the EMS SE, not raw data. And PMU linear state estimator is improving situation awareness. I agree, but I'm also saying in some control centers that operators see the raw data, and the state estimation results, it feeds the security analysis. And so but my point does not change, which is if you want to stop the cyber attack, we have to go to the source, and the source is a big part of the attack source coming from substation. So if you can stop the attack from the substation, then stop it there before it's sent to the control center. So that is the general idea I'm trying to convey. Of course, the attack could be directed towards the control center by itself. And then this question will be, but then when you attack the control center, it might attack the the software there or the IT within the control center. And so it's not the measurement that comes from the substation that's being attacked. So that's a different category. So I hope that response.
We are kind of run out of time, but I have very quick questions. So I want to comment that. So I think in the power grid security definitely is very important. This is when we talk about attacks. But to our knowledge, actually attack is quite real. At least it's not that so common right now. So it's more important is about the reliability or resilience, as you mentioned in your talk. So we just wonder, can we actually extend from the cyber attack to the resilience of the system to enhance the ability of the power grid to like some anomaly detection or something else, instead of just to look at actually this attack from outside or inside? Yeah.
There is an area in the power grid that's normally called cascading events. And that cascading events is known for maybe 10 from about 2000, so 20 years. And so people develop technologies called defense system, trying to protect that power system. And that cascading events at that point, as I said, it was more about the weather-based events or intentional attack. By intentional attack, at that point, it was less of a cyber attack because 20 years ago, there's not much research about cyber attack on power grid. And so that is the new component of that range of attack that we have to address. And that is that's the new class of attack that we have to be able to protect against. And I think that's what you're saying. And what I have shown here is how do we do that? That's the question, right? Well, because the nature of the attack is cyber, and it's integrated cyber and physical system. So we have to have the tool to do the study. We have the technology to try to mitigate that. And that's why we talk about this intrusion detection or this integrated cyber physical system security technology.
Mm-hmm. Yeah, that's why, with NERC, you have the testbed, right? You have this simulator which make this research possible.
It's all software though, so it's about, it's very, in the power business, it's very hard to have hardware testbed because you have to buy a real SCADA, you have to buy a hardware component. That's very hard because the research lab, it's very hard to handle that. And so most of our testbed is software, but fortunately we can get the right protocol and right power system simulation and build our own cyber system model. And that allow us to do such study. So that's not too bad. So the real work is to be able to develop the cyber system model and being able to integrate. And actually I teach a graduate course on this. So I give the students a cyber system model, and they know how to find a power system model. And the work is try to integrate that and do what I'm saying and develop something good. And many students actually finish the course and publish papers out of that.
Oh, that's great. Yeah.
I think it's good experience for them.
Yeah. It's perfect actually for the student. Actually, they can do something at the campus before they actually get to the real the job, and they'll go to the work.
We have students coming from the computer engineering side also. They don't know much about power grid, but the power grid has very well established simulator, so they can use it as a black box and trying to figure out a better way to do a cybersecurity protection. Yeah,
and as the one of the most important actually cyber physical system, I think a power grid and this testbed and this simulator is very important for people to do that. Yeah, and I think, Professor Liu, because we are kind of run out of the time, so we are going to kind of stop here. And we really appreciate actually your coming to give us this kind of the talk. And that's great action for people to, especially actually a lot of people interested in the CBS. We do not have too much background about the power grid. That's why we learn a lot. So really appreciate that. Thank you very much.
My pleasure. So I hope next time I will be visiting the campus and meet some of you. So
of
thank
course,
you.
and then we will own your actual dinner for sure. Yeah.
Great, excellent. Well, take a rain check for dinner.
Yeah, of course. And thank you for everybody for coming actually to this talk. And then we will see you next Wednesday afternoon. Yeah.
Thank you very much.
Yeah, thank
Bye.
you very much. Bye-bye.